Hi guys, how's it going? Terry Brown, Mechanical Engineering here with another engineering mechanics video. This time we're going to look at frames and machines problem, particularly a machines problem, and we're going to look at a toggle clamp. So let's have a look at the problem. Okay, here we can see the problem. This is probably one of the more difficult ones that I've done. And yeah, so the way, and this video, and the way I've done the solution here is probably not the most straightforward or elegant solution to the problem, but the way I approached it is normally I can see through the solution to these kinds of problems, particularly if there's a two-force member involved. In this problem, there's no two-force members. So in thinking through the problem, it was during a class actually, I came across the problem and I thought, oh, I can't actually see my way through it all the way, right, just by looking at it. So what I did was to just do what I suggest to students to do and just to get started somewhere and see how you go. So let's firstly think through the solution. So when I say just get started and see how you go, I mean make use of the techniques that I've taught you, how to apply or how to draw free body diagrams, how to apply and make use of the equations of equilibrium, taking careful note of pin connections and putting the reactions there, and taking note and taking care of Newton's third law as you look at free body diagrams of the components when they're separated. And if you do that, you should be able to solve the problem, because really there's nothing new here that I haven't shown you before. So we draw free body diagrams, and again I'm using my iPad, so that's why I'm kind of looking down every now and again just to click on the button, apply the equations of equilibrium, solve for unknowns, and in fact let me just go back to that. All right, so I think hopefully you all mostly know this by now. The part that you probably struggle with is with a problem like this is, well, yeah, sure, I know I need to draw a free body diagram, but what am I going to draw a free body diagram of? That's where things start to go awry for students trying to solve a problem like this. So let's work through what I've done here. So usually what I suggest to students to do with a machines problem like this is to start with the component where you have a known load. Okay, so here we're told that the force that the block exerts back on to the toggle clamp was, let me forgotten what that was, let me just go back there, 600 newtons. Okay, so we're told that the force that the block exerts back onto the clamp is 600 newtons, which is of course equal and opposite to the force that the clamp exerts on the block. So let's go back over here. And this is probably going to be a bit of a long video, by the way, because it's a difficult problem. It takes time to solve and takes time to explain. All right, so we start off with the member that a load is applied to. You could have started with the bottom one. Doesn't really make much difference. And as an exercise, have a go at doing that for yourself, right? Instead of using the top part of the clamp to draw your first free body diagram, use the bottom bit. Okay, so I've drawn my free body diagram here. I've put the load on, I've put all my dimensions on, I've labeled the important points, and now I've started to think about the reactions at the points where I've removed the other things that were connected to it. So we've got this top handle here that was connected at point A, and I've already started to put on here, because this is a pin connection, we hopefully know that we're going to have two force components there. Really, it's just a single force and some unknown direction, but for convenience and for ease of writing out the solution, we often break that up into components that are horizontal and vertical, because usually we're given all of these dimensions that are horizontal and vertical. Sometimes we're not, and we need to do something different, but for most problems, this is what we have. All right, so I haven't put any arrowheads on here yet. We'll have a think about that as we work through it. So So here I've put on the arrowhead for the vertical component. How have I come up with that? Well, I've imagined for now that I've taken moments about point D here. If I got a force going around this, pushing up here, it's tending to rotate the component around clockwise. So therefore I need this one here to go anti-clockwise. It's made a little bit difficult because we have this other force here that also causes a moment about point D. So it's not conclusive, but I have had to think about it and just put my arrowhead here. If you don't know, and as you'll see as we go through this solution, I actually get one or two of these wrong. And I'll show you how I deal with that. Okay, so I've now just put the force components, reactions at point D here. Right, so again, we've got a pin connection here. So we've got an unknown force and angle, or an unknown vertical reaction and an unknown horizontal reaction. Okay, so if I've made this force here going up and this one's going up, then for some of the forces in the vertical direction, this one will need to go down. Here, I've assumed that this force is needed also to balance the moment caused by this one. If you had to put that acting to the right, doesn't matter. And I think actually this is one of the ones that I got wrong. But we can continue on with our diagram as we first draw it. And then at D, if the force at A is going to the left, then the one at D must be going to the right. So we've got our free body diagram with the forces shown. Let's add on here our labels that we can use in our equations of equilibrium and start to try and solve some things. So usually we'll start with some of the forces about a particular point to solve for some of our unknowns. So here we could choose point D or point A, wouldn't really matter, and in both cases we end up with two unknowns in the equation anyway. So again, as practice, I would suggest you go away and do the same or do the equilibrium equations and take moments about point A and see that you get the same as what I've got. All right, so having chosen point D, let's work through our moment equations. So taking moments about point D here, we've got AY acting vertically upwards, and that tends to rotate the body anti-clockwise, right? Anti-clockwise about point D, so therefore this one is positive. And then we have AX, perpendicular distance from the line of action of AX to point D is 50 millimeters. Again, tending to cause an anti-clockwise rotation about point D. So therefore, this sign out the front here is positive. And then we've got the force out here tending to cause a clockwise moment about point D. So therefore, this one's negative, and its magnitude is F times the perpendicular distance from the line of action of the force to point D, which is of course 140 as shown here. No other forces causing moments about point D, so therefore we can put that all equal to 0. And I've just jumped straight into the sum of the forces equation of equilibrium here because I've got two unknowns. So I can't solve for anything yet. So I've just left that one there for now. So sometimes a student might get to this point and go, oh, I can't solve for anything, and then start to panic. No need to panic, just keep working through. All right, so let's use our next equation of equilibrium, and we've got some of the forces in the vertical direction equal to 0. So we'll have from there, AY is positive, according to what we've assumed here, minus DY plus F, all equal to 0. Again, we've got two unknowns here that we can't solve for anything. So, a student doing this kind of a problem, used to being able to solve for things straight away, might be starting to panicking even more, thinking, oh, what am I going to do? Okay, don't panic, just work your way through. So some of the forces in the horizontal direction equals 0. So we've only got the two forces there, AX and DX, and they're going in opposite senses, so I can just say AX equals DX. Right, you could write DX minus AX equals 0 and then rearrange. You can just go straight to here, but you must put in the sum of the forces equals 0 to justify that. All right, so that's as much as we can do there. Right? We can't solve for anything yet. All right, so let's now draw a free body diagram of something else. So I've already written here that I'm going to draw a free body diagram of the upper handle. We could have maybe drawn a free body diagram of this lower handle. That might have worked better, but I chose the upper handle because it's got this force here, P, that we're trying to find. So I decided to use that one. So if we draw that free body diagram, we've got the load applied out here, our points A and B. So now we need to think about what we draw here on A and B. All right, so I can't remember what I did first here. So I started with this force down here, Bx. So the way I did that was to, well, firstly, we know that these 2 points here are pin connections. Right? A and B here are pin connections. They're not two force members, right? Because we've got 2 connections, then a force out here, 2 connections and a force out here. So it's not a 2 force member. And these are pin connections. So the best we can do is to just draw our horizontal and vertical reactions. Right, so I've started with Bx by imagining that I'm taking moments about point A here. P will cause a clockwise moment about point A, so therefore the force here at B must be anti-clockwise, must be causing an anti-clockwise moment for equilibrium. So therefore Bx needs to be to the right. All right, so now I've put in the horizontal force here for the reactions at A. Now at this point, you might be, if you're rushing through and not thinking carefully about what you're doing, you might be tempted to put an arrow here facing to the left, right? Because we've got the arrow for Bx facing to the right or heading to the right. What you need to do here is to look back at what you've drawn on the first free body diagram that we had. Okay, so here we made some assumptions about the directions of the forces. When we draw a body that was connected to this one, we must obey Newton's third law. Okay, so what we draw here at A on the free body diagram of the upper handle must be equal and opposite to what we've drawn at A on the upper part of the clamp. Must obey Newton's third law. So there we have to put the arrowhead this way. So now we can see that, when I did this from scratch, right, and this, what you're seeing here is what I did from scratch. Right? I haven't changed anything. So I got to here and went, right, this is going to be the wrong way around. But what I've done is to just leave it, not try and change it. So sometimes I'll see, students with their free body diagrams and they have stuff like this, right? And they've changed their mind about what they wanted to do. Right? And then they don't scribble it out properly. It just is a recipe for making a mistake in your solution, right? So there's actually no need to change it. You can actually keep working through with it in the wrong sense, okay? All right, so we've labelled that AX there, and then with AY, we got the same thing, right? We need to obey Newton, whoops, not meant to be drawing down there. We need to be obeying Newton's third law, so what we've got down here, AY is opposite to what we've got up here. Okay. And then Bx, we can look at our other 2 vertical forces and we can be pretty sure that that one, By, is going to be acting upwards. All right, so we've got another free body diagram. Now we can start applying our equations of equilibrium. So some of the moments about a certain point, again, I've given away what I've done. Right, we could take moments about point A. and solve for Bx directly here. I've chosen, for whatever reason, to use point B. So let's work our way through the equilibrium equation. So we have moments about point B here, AX tending to cause a clockwise moment or rotation about point B, so therefore it's negative, and its magnitude is AX times the perpendicular distance, which is 50. And then we have the force out here on the handle, P, times its perpendicular distance to point B, which is 140, also tending to rotate clockwise about point B, so negative, and no other forces causing moments about point B. AY passes through point B, so that doesn't cause a moment. So again, we've got an indication that this AX arrow here is going the wrong way. Again, I haven't tried to change it. I've just left it as it is, and I'm going to work my way through the equations of equilibrium. All right, so now if we rearrange this, we get AX is equal to 14P over 5. So now I'm starting to label my equations because I want to make use of them and start substituting things in. Okay, so I can substitute this AX up into these equations up here and start to solve for some of my unknowns. Right, so if I substitute equation 4 here into equation 3, then I can solve for dx. Well, not so much solve for it, but get dx as a function of the thing that I'm actually trying to find in the end. Right, so we know this force over here, F, P is what we're trying to find. Right, so it's in this example, I'm just working my way through the problem without really knowing exactly what the path is to get to what I want to find. Right? But I'm just doing my calculations, applying my equations of equilibrium, keeping it all nice and neat and clear and in a logical order until I find something that's useful. Right? So now I've said, okay, we've got this one here, AX is in this equation, so I'm just going to substitute that into there, and I get this equation. So I've got AY and P still as unknown, F is the applied load. So if I rearrange that, I now have AY as a function of the applied load F, the applied load F in here, or the known load F, and we want to work out the force P that we need to apply. All right, so still haven't worked out much yet. At this point in time, if students were doing this, they're starting to panic, especially if it's a timed exam or quiz or something. But you don't need to panic. Right? You can just keep working along and keep doing the same thing. All right, so let's choose another body to draw a free body diagram of until we get something that works. All right, so now we've got a free body diagram or partial free body diagram of the lower clamp here. Right? And as I said, this is not meant to be the elegant solution, how to solve this in 3 minutes video. This is kind of modeling how to deal with a difficult problem like this as a student just learning how to do it. All right, so we've got our lower part of the clamp, drawn the body, we've got our loads on, we've got labels where the points of importance are, got some dimensions that we can clearly see where they're going. And again, we've got at point D here, we've got a pin connection. Right, now here, we need to be careful. What did we do on the previous page? Right, we drew a free body diagram of this on the previous page, and we would have drawn some forces here. All right, so I'm going to have to quickly go back and look at that and just see what I've done here. Right, so on the free body diagram over here, we've got down and to the right. So on the lower part free body diagram, I'm going to have up and to the left. Okay, so let's go to there. Right, so that's what I've got, right, up and to the left. Okay, so then at point C down here, again, another pin connection. So two reaction forces, call them CX and CY. We need to work out the sense of those forces. So I can't remember which order I've done. So I went to CX over here is to the right. So if DX is to the left, CX will be to the right. If you take moments about point D here, the force out here, F, is causing an anti-clockwise moment about D, so we'll need CY this way. Okay. Again, if you can't work out these just by doing that thought experiment, don't worry. The CX and CY, we haven't done any other free body diagrams that involve this point yet, so we can try and work it out like I've done, or we can just assume the sensors. And then when we draw if you have to draw the free body diagram of this part, then you need to worry about Newton's third law. All right, so again, usual approach, take moments about somewhere, try and find some of your unknowns. So here I'm taking moments about point C, and we'll get an equation that has F and dx and dy in it. And on the previous page, we had some expressions for dx and dy from the previous free body diagram. So let's do this. So we've got force out here times the perpendicular distance from the line of action to point C is 140 plus 65, right? And again, note how important it is that I've got this C here in my equation of equilibrium, right? I need to be going back and looking at what is here so that I can then, right, tell you what I've done, or you can look at what I've done and try and work it out, right? Without this C here, you've got no idea. Right? All right, so that's that one. Right. It's tending to rotate anti-clockwise about point C, so that was positive. Then we've got dy here tending to cause a clockwise rotation about point C, so it's negative, and its perpendicular distance from the line of action to the point is 65. And then we'll have dx up here tending to cause an anti-clockwise rotation about point C. Perpendicular distance is 50, so that goes in there, all equal to 0. And from before, we got to this for dx. Okay, so we can substitute that in to the equation. Okay, so note here, right, dx, I got minus 14p over 5. Then when I draw this equation, or write this equation rather, right, whether there was a plus or a minus out here depended on the arrow that I've got on my free body diagram. And then I substitute for dx and I include the negative in my substitution here. I've just rewritten this equation here and just substituted directly in. So I can rearrange that equation and I can get dy is equal to f times 205 over 65 minus p times 140 over 65. I've written that in a bit of a weird way, but hopefully you can see the maths there. So what I could have done was to put all of the numerator in brackets and just did divided by 65 outside here. But anyway, that's just algebra. That should be high school maths. Okay, so also from before, we had, right, equation 2, we had before ay minus dy plus f equals 0. All right, so I should have probably numbered this, called this 5. So let me do that. Equation 5. Right, and this obviously would have been easier to see if it was all on the one page. So then we say substituting ay and dy into equation 2, we have up there, we can get that expression. Okay, so we've now got an expression that has only f and p in it. right? So F is known. So if you prefer, you could put in a number at the start rather than trying to carry F all the way through. But you know, I think you should try and get used to carrying parameters from the problem through the equations like this, because if you want to put this into an Excel spreadsheet, for example, or write a program, then you're going to need to do something like this anyway. We've got this expression at the end here. I've just copied that across to the next page so we can refer to it easily for rearranging. Right, so we just need to rearrange that expression, and that's all I've done to go from here and here, just some algebra. And F was equal to 600. That's our given load. Yeah, put 600 into here, divide, multiply by this, divide by this, and we get P equals 80 newtons. How do I know that that answer's right? How do I check my solution? Let's now look at a way we could do that. You get to a number like that, there's been a lot of steps, a lot of substituting here, there, and everywhere. I've had to make sure I substitute a negative value where it was necessary. I need to make sure I've obeyed Newton's third law when drawing my free body diagrams. So there's lots of opportunity for things to go wrong in this solution. So let's have a look at my check. So what I'm going to do is to work backwards now from my answer. So I got P equals 80. So I got up here P equals 80 as my answer. Now I'm going to work through the problem as if the question was, if I apply 80 newtons to the handle here, what force do I get on the block? So if we go back again to the picture of the problem. All right, so now I'm going to redo the problem, but say using my answer that P is equal to 80, I'm going to work out the force that's exerted on the block. So let's do that. So there's free body diagram of the upper handle, same as we had before. And if we take moments about point B, we can determine AX straight away. So let's put that in. So minus AX, so about point B, AX is going or tending to cause a clockwise rotation about B, so AX times 50, clockwise, so it's negative. P is also tending to cause a clockwise rotation about B times perpendicular distance, so a 40, and so that's negative, and again we get AX equals minus 14P over 5. Right. If I had have started with this free body diagram the first time I did it, I might not have assumed that the force here was to the right. But yeah, as I've shown, it doesn't matter, right? As long as you do work through it and are consistent and follow the rules as you work through. All right, so here I get AX is minus 224, and this way might be a little bit easier to understand because I'm starting to find numbers straight away. All right, so we've got AX equals 224, negative. Let's look at some of the forces in the horizontal direction equals 0. So here, again, when students get a negative answer here, the temptation is to go back and try and change the sense of this arrow. My strong recommendation is do not do that. Just leave it as it is. Because if you go back and change this arrow, this equation here becomes wrong. Right? Unless you change this equation, right? And then you've got to change it here, right? And you just get lost, right? And you'll miss a sign somewhere, guaranteed. All right, so looking at the forces, we've got AX plus BX equals 0. We can rearrange that and say BX equals minus AX. All right, so this here, right? The pluses and minus here, or let's go back to this line here first. The pluses in front of the terms here come from looking at the arrows and looking at what you've defined here in your equation of equilibrium. This next first part of the equation comes from algebra, right? You put AX on the other side here, it becomes negative. Now, when you substitute a value for AX, you substitute in this value that you found here, right? So you can see what I've done here. Okay, so BX becomes positive, right? Which is correct, right? So here, from your algebra, the plus or minus here tells you whether you put your arrows in the correct direction or not. So if AX here is actually going to the left, as indicated by the minus sign, then BX must be going to the right. It's tricky, I know, and can become confusing, but that's the explanation of how it works. And really to get good at it, you just got to do lots and lots of problems and do problems in multiple ways to see where your errors are, right? Or if you've got a textbook with work solutions, or if you in my classes, you've got Canvas site full of work problems. Have a go at doing the problems yourself first, and then look at the answers to see how it's been done and to see whether you've got it right or not. All right, so let's look at some of the forces in the vertical direction. Equals 0, we have By in the positive direction, Ay going down, so that's negative, P coming down, so that's negative, so that's our equation of equilibrium. Okay, so now free body diagram of the lower handle, and we have similar to what we've got over here. So we need to see if there's anything else this is connected to, and yes, it's connected to the first free body diagram over here at B. So we need to obey Newton's third law there. Right, so we've got those two reactions, and they need to be equal and opposite to what we've got over here. And then at C, we've got pin connection again, vertical and horizontal components of the reaction force at C. If we go through process and think about which way they're going to go, right, I've just put them the same. I do a free body diagram of this before? I can't remember. It's been too long, and I don't want to flick back. But anyway, you can go through the process of trying to work these out, or you can just put them in directions that you think and then see what happens after that. So now we need to think about where we take moments about. So we've got Bx. We don't have Cx or Cy. We don't have By, so let's take moments about C and see what we get. So we've got Bx, we found Bx before, so we should be able to calculate for By, right? So we've got Bx times 50 going anti-clockwise about point C. And we've got P times 140 plus 20 is 160 going anti-clockwise, so that one's positive. And then we have By times 20 tending to cause a clockwise rotation about C, so that one's negative. So therefore, rearranging that, so just algebra here, rearranging and then substituting for Bx is 224 that we found here, times 50, and P was 80 times 160, and dividing by the 20 from here gives us By, which we calculate to be 1200 newtons. So then if we do sum of the forces in the vertical direction equals 0, we get Cy minus By plus P. Okay, so all of these signs here in this equation come from the free body diagram and what I've defined as positive. So rearrange that and we get Cy equals By minus P. So put in the 1200 that we just found, and P that we've got as our known load now because we're checking our answer from before. And if we do sum of the forces in the x direction equals 0, we get minus Cx minus Bx equals 0. So Cx equals, so just algebra, Cx equals minus Bx. Bx here was 224, so Cx is minus 224. right? Which again, we can see from our free body diagram, right? So Bx is positive value. So this arrow is in the correct direction. And then, because our arrow here for Cx is to the left, and they're the only two horizontal forces, we must get negative for Cx here. Okay, so the negative that we get here indicates not that it's going in the minus y direction, but that it's in the opposite direction to what we've shown on our free body diagram up here. If we now look at a free body diagram of the lower clamp, because we still haven't gotten to the force here yet, which we're trying to calculate. So before we do that, I've just copied over here the free body diagram of the lower handle. I just copied this here for reference, so I don't have to flick back to the previous page. And this is what we got. We got Cx equals minus 224 and Cy equals 1120. Now, when we draw our free body diagram over here, I've started with dx and dy. These are unknowns. At C, it's important what we do here. All right? So here, we need to, again, make sure that we obey Newton's third law. And we draw the arrows here opposite to what we've got drawn here. Right? Even though this says negative here, don't worry about that. Right? Just draw the forces equal and opposite to what they are shown over on the other free body diagram. Okay, so now that we have our free body diagram, so at D it was just a pin connection. And again, I don't think I had a free body diagram with D in it on the previous page. If I did, then you can go back and check that these are equal and opposite to what I've shown on free body diagrams previously, or else you can just put them whatever sense you like. All right, so let's take moments about point D and see what we get. If we do that, we look at the forces that we've got here. So we've got force here, moment about point D, which we've chosen, F times 140, going anti-clockwise, so that one's positive. Then we have looking at the arrow, forgetting about that this is negative over here, right? Just looking at the arrow, we can see Cx times 50, and it's tending to cause an anti-clockwise rotation about point D. So therefore, this one's positive. And then Cy, perpendicular distance to point D, is 65 here, and it's tending to cause a clockwise rotation about point D. So therefore, this one's negative. And then if we substitute these values from here into here, okay, so firstly, I've just rearranged this equation. And then when we substitute our values, right, we substitute here, so Cy is 1120, so we substitute that in, and then Cx, we have to substitute the negative value in here. Okay. Now, if you don't do it the way that I do it, and you try and change signs and things on the way through, and change arrows, right, there's a good chance that you'll get this sign here wrong. Right? And if you do, then you get the answer wrong. So if we do put that into our calculator, we get that the force is 600 newtons, and we've now got some confidence in the fact that we've likely done our calculations correctly. Right? Doesn't guarantee that they're all correct, but it's more likely that they are. Right? We could have made an error that we've carried through in both problems. Yeah, in not so much in this problem, but I've seen previous problems with students where they had they might have had a force like this as a load, as a known load. It might have been 300 newtons or something, and then they had to work out this angle here, theta, and they got this angle wrong. And then they calculated their components, and so if they got this angle wrong from their trigonometry, these are wrong, and then that's carried through both your first solution and then your check solution calculations. You could do that, right? The check's not going to fix this problem, right? You're just going to have this same problem in both solutions, right? So I often see students write at the end of their solution, when they get the same answer like that, they'll write, therefore the answer is correct. No. Therefore it's more likely that it's correct. But if you've made this kind of error with the loading, then both answers are incorrect. But that's not the case in this problem, so we can be a bit more confident that we've actually solved the problem correctly. All right, so that was quite long and involved and maybe a little bit hard to understand, but hopefully it's instructive to show you how you can get these difficult problems correct, even though you might have not started out in the best way. And it also shows you how you can solve the problem in different ways and still end up with the same answer. Anyway, that was a long one. See you next time. Bye for now.